Hey guys, welcome back to Business Stats. In this video, we're going to cover the normal distribution, which is the last thing that we're going to cover in modules 4 and 5. So this is the kind of focal point of our continuous random variables, our continuous distributions. This is the thing that is going to be covered and used most often throughout kind of anything. This is the, I'm not going to call it an intuitive distribution, but it is certainly the most useful distribution that we use. You're going to see this in business analytics. You're going to have to kind of understand how things relate to the normal curve, the bell curve nature of it. You're going to have to understand z-scores. And yeah, this is just something that, I mean, you've probably already seen this. I mean, we touched on this a little bit, and I think it was module 2 or module 1, back a few weeks ago. But this is going to be something that you're going to need to be very familiar with, and this is something that is really nice to be able to teach and kind of give you guys, because it's something that is truly transferable. Whereas a lot of these things, we'll look at and we'll teach, and yeah, it's good to learn it for this class, and it's good to learn it computationally, and yeah, it sort of helps your analytical skills or whatever. But 5 years down the road, you're never going to be calculating, a Poisson distribution or a binomial distribution. Chances are, that's just not ever going to be the case. And if you are in a field where you're doing that, you're going to be using some computer to do the computation, and it's all going to be given to you, okay? But the normal distribution is something a little different in that, it's just really useful. It's just really, it permeates not just business statistics, it permeates many walks of life, and ultimately you're just going to benefit a whole lot from kind of just understanding the way that something operates off of a normal curve. Okay, so let's get started on that. In the notes, or in the PowerPoint slides, I think that we gave you, it gives you the big long normal distribution PDF function, the probability distribution function. We are not going to worry about that function at all. Okay, so you shouldn't have to do any computations on that probability distribution function. What we are going to use to do our computations, a lot of the time is going to be z-score and just looking at the tables. Okay. So you need to know how to do things based upon these tables and based upon calculating and manipulating z-score. Okay, so let's just walk through this definition if you're following along and writing with me. A standard normal random variable is a normally distributed random variable that has a mean equal to 0 and a standard deviation equal to 1. So that now we're talking about standard normal. So there's a difference between a normal distribution and a standard normal distribution. Okay. A normal distribution can have any mean and any standard deviation and just be defined as distributed normally. Okay, so we could have anything that's, that follows a normal distribution. Standard normal, or what we call standardizing, is when we take the qualities of a normal distribution and apply and calculate a z-score. What the z-score is putting it into the units of the standard normal curve. The reason that we want to do that, okay, it's to put it in the units of the standard normal curve, is so that we don't have to use that crazy probability distribution function. It's so that we can use our tables to do all of our calculations and kind of use a more obvious, pure logic on solving these problems, okay, as opposed to going through and kind of banging our heads against the wall trying to do really, really complicated math that's much more complicated in computation than even the binomial that we saw in a video or two ago, or Poisson or anything like that. Okay, so we don't want to have to use that. So what we do is we take whatever distribution that we're working in and we standardize it by using this z formula that you see on the screen, and that's that. And it makes things easy. Okay, so enough said about the z formula. We're going to get to that in a couple of problems here. But these examples in this U-try here that I'm showing you, these are examples of just flat out using the standard normal curve. Okay, so notice that the variable that's used inside of the probability is z, okay, not x. And And so this is assuming that we're working with standard normal, meaning that mu is 0 and that standard deviation is 1. Okay. So let's work through some of these. I know when I talk through these distributions, you might feel a little bit lost or whatever. But I think once we, like as always, once we get into the examples, it makes it just kind of a lot easier to see what's going on. Okay. All right. So let's introduce you to what the tables look like. Okay. So these tables I've now explained in a couple different videos of where you can go to find them. It's just your content tab, going down to resources, and then going to probability tables. Okay. So here's we see the standard normal probability table, okay, and this is the positive side of it right here. So we see z-scores, the z numbers over here, with all positive values, okay, and here we see z-scores with all negative values. So these are not probabilities. The z-scores are not probabilities. The z-scores represent the number of standard deviations an observation or a point is away from the mean. Okay? So if we have a negative z-score of negative 2.6, that means that we are a negative 2.6 standard deviations away from the mean on the left-hand side, right? Because it's negative. So if our mean is 0, our mu is 0, and it's in the center of a normal curve, we see this pictured normal curve up here, then a negative z-score tells us that we're working on the left side of the normal curve. Okay, so that's what this negative number means in the z. It is not a probability. It means that we are negative 2.6 standard deviations away from the mean on the left-hand side, or 2.6 standard deviations away from the mean on the left-hand side. Conversely, on the right-hand side, looking over here, we are on the right-hand side. Okay, so we look here. So we have 3.1 here. That means for this line in here, we're 3.1 standard deviations away from the mean. Okay, that's what the z-score stands for. Now, these numbers inside of the table are probabilities. Okay, so these represent areas under the curve. Okay, areas under the curve. So the way that this table is set up, okay, it is the cumulative areas under the curve, meaning we're starting from left to right on both tables, okay? So you'll notice that we look at this table, we have a z-score that is on the right-hand side of the curve, but it's giving us the area all the way up to that point, right? So cumulative. It's giving us the cumulative area under the curve. Okay, so all of these numbers, as you would expect, are going to be over 50% because we're at least going to have the left-hand side of the curve there, and we notice that. So at a z-score of equal to 0, it's 50%. Okay, and so as we get further and further away from the mean to the right, we're encompassing a larger amount of area, right? So as z moves to the right, we're going to get a bigger area under the curve here, and then thus the numbers get bigger and bigger and bigger and closer to 1, right? Because the total area under the curve is 1 because it's a probability distribution function, okay? So then on the left-hand side, we're gonna see numbers that are all smaller than, or 0.5 or smaller, okay? So that's what we see here, and they go all the way down to 0 as we get further and further away from the mean, because this sliver of probability gets really tiny, okay? So remember, this is a probability distribution function. It's a curve, and the area under the curve represents all of the probability contained. So the total area under the curve is 1, and the smallest amount of probability that you could have is 0. The negative numbers in this are not probabilities. They're amounts of standard deviations away from the mean. Okay, that's our z's. Okay, so that's a lot of words. Now let's actually put it into action. Okay. All right, so let's look at number 1. So this number 1 is asking us calculate the probability that z is between 0 and negative 0.9. Okay? So we're looking at this one. Z is between 0 and negative 0.9. Okay? So let's just first get here. All right, so 0 is the same as negative, 0.00 or whatever. Okay. So what we want to do is we want to recognize that when we calculate probabilities, this table is only going to give us cumulative probabilities, meaning it's going to give us everything up until that point, right? So what ends up happening is we're going to get a number visually, right? We're going to get a graph of a probability at some point that looks like this. And it's going to give us a number associated with that, a probability number, okay? When we're talking about an interval. And then we're going to get a graph that looks like this. Okay? And it's a question saying, well, what's the probability that z is between the two? Okay? And we can think about it like, well, we have this z value right here, and if we minus off this z value, it's going to give us the area in between. And that's going to be representative of one of these like intervals that we're talking about, like this, say this negative 0.9 is less than z is less than 0 sort of deal. So this is the concept that we're talking about. Because the table is always giving us cumulative, right? We're gonna think about this in terms of, well, we can't just calculate this straight away. We actually have to go in and we have to pull a full chunk and then minus another full chunk off of it to get this sort of intermediate area. Okay, so let's go ahead and do that for this. So if I'm looking at this first one, I recognize that to say, well, we need to take the bigger probability and minus off the smaller probability. So the bigger probability is going to be the one that's furthest to the right. Okay, don't look at the numbers like from is negative 0.9 larger than 0? So it's going to be the furthest positive number, essentially. So your largest number, okay? So 0 happens to be the largest number in this. So it's going to be the probability. So let me just write this down here. I've got more room. So the probability that 0.9 is less than z is less than 0 is going to be equal to the probability that z is less than 0 minus the probability that z is less than negative 0.9. Okay? So that's that. So now what we have to do is we have to go to our table and we have to find out, well, what are these probabilities? So z is less than 0, that's the easy one, right? We know that like if we're just sitting at the mean, we're just sitting at 0, we're 0 standard deviations away from the mean. We just know that half of the probability is above it and half of it is below it. So we can see this number right here on the table. This is z is equal to 0, okay? So we can go back here and we can say, well, this is just 0.5. We know that, 0.5000. Now we have to find probability that z is less than negative 0.9. So we go back to our table. We have to find z. Where's negative 0.9? Negative 0.9. And it is right there. So we use this first, we use that first number, 0.841. Why do we do that? Another thing to think about with this table is, so this table up here, or this row up here, represents the second decimal in the z value. So if we're just looking for negative 0.9, it's right here. If we were looking for negative 0.91, right there, negative 0.92, right here, negative 0.93, we get that, okay? So 0.841, 0.1841, I should say. And then we just do that math, and that is 0.3159. Okay, so that is our answer for 1. And that represents like the area right here. Okay, that's our area in between there. So what we did was we took this bigger area. So in our case, I guess earlier, this would be more centered because it's, z of 0. But right in the middle here, and we would then minus off the smaller probability, and it leaves us with this interim probability here, okay? Okay, let's do a couple more of these. I don't know if we're going to get to all of them because I think the video would run too long. So we'll just maybe just do 2 more of these, and then we'll move on to the other section. But I think you'll probably get the gist by then. So let's do the second one. So the probability of negative 1.5 is less than z is less than 1.25 is then equal to, remember the biggest one, the biggest probability, which is going to be our biggest z value. Probability of z is less than 1.25 minus probability that z is less than negative 1.5. So now we just have to find these on the table. So 1.25, we go to the table. 1.25 is a positive z value, so it's going to be on the positive side of the table. We find 1.2, we march over to the 0.05, right? So this is representative of the 1.25 z value, and that's our probability under the curve. So we have 0.8944. Okay? So we write that in, 0.8944 minus, now we got to go to the other table, negative 1.5, and that's just negative 1.5 straight up, no more decimals, and we have a 0.0668. .0668. We minus those off, and what do we get? 0.8276. So that's going to represent the area between, or under the curve between negative 0.5 z value and 1.5 z, or 1.25 z value, excuse me. All right, so let's just do 3. And hopefully this will give you a sense of some of the logic here. So 3 is not an interval that like is z is between something. This is just z is more than something. So this is probability of z is greater than now 1.62. Now we know that we can't find a greater than probability in the table. That's important to note, right? So our probability is always giving us less than probabilities because of the cumulative nature of it, because it's always up and to a point, not past the point, not above the point. So but what we can do is we can say, well, we know the properties of this probability distribution function. We know that the total area under the curve is 1. So in order to find the probability that z is greater than 1.62, we would just say, well, this is just equal to the total probability minus the probability that z is less than 1.62. Okay? So it's just going to be 1 minus, and then now we can just go to z of 1.62. So on the positive side here, so we find 1.6. We march over to 2, and we get 0.9474. Okay? So we put 947.9474, and then 1 minus that is just going to be 0.0526, and that's that. So this would be the probability that z is greater than 1.62. Cool. So that is just a general way to deal with calculating probabilities using the z-tables. And you will have the z-tables on the test. That's not going to be a question of that. So, all right, let's move on to some applications. So now this is where we're actually going to use our z formula to obtain our z values. So we're taking something from a normal distribution to a standard normal distribution, such that we can use those tables. Because if we didn't do this process, we would have to calculate it using the crazy formula, and that's just nonsense. There's just no way to, or there's just no reason to do that. Okay. Example 1: a new gas-electric hybrid car has recently hit the market. The distance traveled on 1 gallon of fuel is normally distributed with a mean of 65 miles and standard deviation of 4 miles. Find the probability of the following events. Okay? I think you'll get pretty comfortable with how these operate. So I'm just going to write down the information that we know. We know that mu is 65, mu being the mean, and sigma being standard deviation is equal to 4. Okay? So now we need to calculate, what did it say? Find the probability of the following events. A car travels more than 70 miles. So x is more than 70 miles. Okay? Or a car travels less than 60 miles, it's saying. So x is less than 60 miles. So these are 3 separate problems. I'm just writing them all out at the same time. Or car travels between 55 and 70. So 55 is less than x is less than 70. Okay, so for all of these, we want to convert to standard normal by finding a z-score. So let's just do problem A. Problem A here. or problem at symbol. Problem A. We want to find the car travels more than 70 miles, right? So let's first find the z-score of 70 miles. So we go up to our z formula that we learned on the last page. Z formula is equal to x minus mu over sigma. And I think we learned this in a previous module as well, or we at least touched on it. X minus mu over sigma. So our x value is our 70 minus our mu, which is 65, over sigma, which is 4. So we get 5 over 4, or 1.25. And so now we just turn this into a problem that we had before. Now we want to find, okay, well, what's the probability that z is greater than 1.25? Okay, well, we know, looking at because we have cumulative probability on our table, this is just equal to 1 minus the probability that z is less than 1.25. Okay, so we just go to our table and we want to calculate the probability, or we want to just use our table to find the probability that z is less than 1.25. So we just go to our table, we're on the positive side, 1.2, 5.8944. So we have 1 minus 0.8944 equals 0.1056. So that's our probability. That's our answer to A. B, car travels less than 60 miles. Okay, so let's first find our z-score. 60 minus 65 over 4 is equal to negative 5 over 4, which is equal to negative 1.25. And we want to know probability that z is less than negative 1.25. Okay, and we don't need to do any manipulation there because we have a less than probability, so we know that our table is going to function accordingly. So we go to negative 1.25, negative 1.2, all the way over to 5, which is 10.1056. Look familiar? It should. It's the same probability as our last one. Not surprisingly, so like in our last one, we had the z-score of 1.25, and we calculated the area above it, so the tail above it, and that was 0.1056. Now we have negative 1.25 as a z-value, and we calculated the area below it, also 0.1056. So these tails are equally the same size, and that makes sense because one we have a negative z-score, and the other one we have a positive, and we're calculating the area beyond those points on the curve. Okay. And then let's do C. So we're going to have to calculate two z value, or two z scores for C, even though actually we already calculated the one in the first problem. So we'll just calculate the other z value here. So z is equal to 55 minus 65 over 4. Negative 10 over 4 is equal to negative 2.5. So that's 1, and then we already know the top end z-score for 70 of 1.25. So now we're just saying, well, what's the probability that negative 2.5 is less than z is less than 1.25? Okay, and this is just going to be the probability that z is less than 1.25 minus the probability that z is less than negative 2.5. Okay? We know our probability that z is less than 1.25, and that is our 0.8944, because I have already found that in the problem. And then our z is less than negative 2.5. We find that here, negative 2.5, 0.0062. 0.0062, and that is going to equal, if I can write it in, that is going to equal 0.8882. Okay, so that's that. me know if you guys have questions on that. We're just going to try to fly through these examples because I want to get them in, and I don't want this video to be like an hour long. So yeah, as always, you'll shoot me questions if you have them, or if I didn't explain something correctly, or if I misspoke and led you in the wrong direction. So certainly give me questions and feedback. I appreciate that. All right, example 2. How much money does a typical family of 4 spend at McDonald's restaurant per visit? Jeez, I seem to talk about like McDonald's and Taco Bell in this in this class too much. That's probably not a good sign. Anyways, all right. How much money does a typical family of 4 spend at McDonald's restaurant per visit? The amount is normally distributed with a mean of 16.4, standard deviation of 2.75. All right. So find the probability that a family of 4 spends less than $10. Okay, so this is easy given what we just learned, right? So we have a mu here, we have a standard deviation, a sigma, and then now we have an x value for A. So let's just find the z-score. 10 is our x, 16.4 is our mu, all over 2.75. So we get negative 6.4 over 2.75. And then that's going to give us a negative 2.33 z-score. All right, so now we want to look at, we want to know how much, how likely, what is the probability that they spend less than $10. So it's going to be, what is the probability that z is less than negative 2.33. Okay, so this is easy. Now we know how to do this. We don't have to do any manipulation on the table because it's a less than z-score, or less than probability. So we go over here to the negative side. We look for a negative 2.3, walk on over to 0.03, so negative 2.33, and we get 0.0099. Okay, so that's that. So that is roughly 1%, right? So it says find the probability that a family of 4 spends less than $10. The probability is 0.0099, or just slightly under 1%. Cool. Now, this is a little bit of a trickier problem in B. What is the amount below which only 10% of families of 4 spend at McDonald's? So this might not be obvious, but this is asking you to figure out the amount, right? So now, think about what it's asking you, right? And it's talking about 10% of families spend this. So now what are we looking for? We're not looking for a z-value. We're not even looking for probability because we're given a probability. We're saying we assume that 10% of families are going to spend less than some amount. Find that amount. Well, what is our amount when we look at our z-score? We write our z-score here. Our amount, sorry, that's not a negative x, that's a, yeah. Our amount is our x. So they're saying use this formula and solve for x. Okay, so we have our mu, we have our sigma, but we can find our z, okay, because it tells us 10%. So let's find our z. So let's find our z that corresponds to 10% being below it, okay? So now we go to the z table. So this is different, guys. So like this is going to be an important concept because this is not us looking up a z-value, or this is not us looking up a probability from a z-value. This is us looking up a z-value from a probability. So what we want to do is we want to find 10% in this table. Okay? It seems daunting given the amount of numbers in here, but remember that these things go in order. So if we were to go from left to right on this left-hand side, we're moving down, right? So we're kind of move down to 10%. So you can start here, kind of move up, so you get closer to 10%. Oh, we're at 11% here. Move over, getting closer, and we can just stop at like right here. So we have 0.1003. So what's our z-value there? Looks like it is negative 1.28. Negative 1.28 is right around 10%. And this is fine to estimate at this point. You know, you're not going to get exactly 10%. Negative 1.28. So we go to our table and we find that the z-value that we're using is negative 1.28. So now it makes this problem a little bit, well, it makes it a lot easier. It just makes it like, you just plug everything in. So now we can say implies negative 1.28 is equal to x minus our mu, which is 16.4 over 2.75, right? And so then this implies that x is going to be equal to negative 1.28 times 2.75 plus 16.4. And then thus we further compute here, and x is equal to $12.88. So now it is important to recap. What does this mean? What is the amount below which 10% of families of 4 spend at McDonald's? So we're saying that we believe, given this information, that 10% of families spend $12.88 or less at McDonald's. That's that. That's what that means. Okay? 10% of families, so on the bottom end, 10% of families are going to spend $12.88 or less at McDonald's. Cool. Hope that makes sense. All right, now third example, and then we are going to get out of here, is this. Mensa is an organization whose members possess IQs that are in the top 2% of the population. It is known that IQs are normally distributed with mean of 100 and standard deviation of 16. Find the minimum IQ needed to be a Mensa member. Okay, so let's just think about this. So Mensa, so this genius organization, is this. And they're saying that Mensa members are way up here. Okay, they're in this little tail with the top 2% of the population. Okay, so if we think about it like that, how much of the population is below that? Well, if they're in the top 2%, the rest of us are in 0.98 and the 98%, right? So this is going to help us establish what our z value is. So this is a very similar problem to the last one in part B. Okay, so what do we know? Well, we know what sigma is, or we know what mu is, and that is 100. We know what sigma is, that is 16. And now we need to find what z is, because we want to know what their IQ is. So we're ultimately looking for what x is, okay? All the while we're using, our standard z formula here, okay? So we're going to be looking then for a z value where either 2% of the population is above it or 98% of the population is below it. The reason why I wrote it out like that, so they give us the information saying, oh, well, they're in the top 2%, so meaning 2% of people are above that. But it's easier for us to look at the table and say, well, okay, where's the z where 98% of the information is below it, okay? So I'll just say look for 98 or 0.98 in table, okay? So we go over to our table. Okay, so let's go over to the table. And we're going to look for the point where 2% is above our z value or 98% is below it. So I think it makes more sense because we can just look for 98 in the table. So we start from here, we kind of move up till we start seeing some things close to 98. Oh, here we are, 0.9893. Oh, we're going the wrong way. 0.97, we passed it, so we go over. Boom, there we are, 0.9803. So it looks like we are at a z value of 2.06. 2.06. So we have a z value of, let's say 0.98 is equal to 2.06. Thus, we can solve this problem, right? So we just plug this into our z formula. So we have 2.06 is equal to x minus 100 over 16. And that implies that x is going to be equal to 2.06 times 16 plus 100. Whoa, I don't know what happened there. So that's a 100. Is equal to 132.96, but I think that they only count in whole numbers, so we can kind of round this to 133. So that's that. So what does that mean? What does that number mean? So it asks us, find the minimum IQ needed to be a Mensa member. So it seems like our minimum IQ here is 133. So anybody with an IQ above 133 can be in Mensa, given our, kind of theoretical problem. Okay, guys, I know that this is a lot, like I said. Honestly, I think, modules 3, 4, and 5 are some of the toughest that we cover in this course. And so I get that you're going to have a lot of questions. I'd love to hear them. Shoot me some emails, as soon as you can. But yeah, thanks so much for watching the video, and I look forward to hearing your questions and talking to you in the discussion board and whatnot. All right, thanks so much, guys.